Testing. Okay, 1 second. Second as I get set up. Okay. All right. Yeah, sorry about the interruption. Had to take a bathroom break. Okay. So, as I left off before I had to sign off for a minute. Okay, so as I was saying, there are different types of graphs. Okay, this one's called undirected. Okay. I also hinted at multi-graphs. So what a multi-graph would be is that you can have multi-connections between nodes and edges. Okay, so that's a multi-graph. This is an undirected graph. So graphs can be undirected or directed. Okay, I'll make this example a little. Okay, so for a directed graph, you can go from A to B, but not B to A. Okay, you can go to B to D, but not D to B. Okay, well, you can go from D to B directly by saying, okay, I'm at D, I can go to A, I can go to B. Okay, so there's a special type of directed graph called a DAG, or directed acyclic graph. Okay, in this case, there's a cycle here. Okay, so what a cycle is basically a cycle is you can go from B, D, A, B, D, A, B, D, A, so it cycles. Okay, so an acyclic graph is you remove this edge, you can't just get there's no more cycles in the graph. Okay. So edges can also be weighted. Okay, edges can have weights. So like in my first example in the other video before I took a bathroom break, my very first example I had a graph of Atlanta, South Carolina, the ocean. So in a typical map graph like that, you might want to represent edge weights with the distance in miles between them. Okay, so you can have this one be 3. You can have this one be 1,000. 1, 2, and 3. Okay, and yeah, you can have edge weights here too. Okay. Okay. Let's see. Okay, hang on 1 second. Okay. So in these cases with the edge weights for your adjacency matrix, you can represent that by just storing the weight of the edge in the corresponding element. Okay. And for a directed graph, you can have, let's do a simple one for this one. Okay, here's A, here's A. So in the directed graph, to represent this adjacency matrix, we say AB. Okay, so let's say this is our starting and ending. Okay, so we start at A and we want to go to B. Start at A, go to B. Okay, so here we'll store 1. Okay, but now there's no way to get back from B to A. So you can have this be like infinity, or some value to let you know that there's no way to get back here. Okay, you can even use 0 in this case. Okay. Okay, just use some special value that's not used by anything else. So using 4 for this would be a bad example. Would be a bad thing to put in there, because then that would be representing an edge back to A with 4, which we don't want. So just use some special number that's not being used, that's outside of the domain of the things you're representing. Okay. So I'll complete this example. We're going to want to go from A to C, A to C, A, B, C, this will be 3, C, B to D, which will be 4. A, B, C. Whoops, that 3 should be here. Okay, and that is our adjacency matrix for a directed graph. Okay, so as I was saying with the multi-graph, there's no you don't have to actually store, instead of using a number here, you would have to store a list. Okay. Okay. Let's see. Check the notes. Okay. Okay. So I'm going to branch off onto a different topic now. Okay, so today we've been talking about many data structures. Okay, I'm going to throw some more at you. Okay, so the next data structure is a stack. Okay, so the best way of thinking about a stack is think of a stack of plates. Now, don't think of a stack of plates in like your cafeteria, okay? You know, ones with like a little spring-loaded thing at the bottom, okay? So don't think of a stack like that, okay? Because with the spring-loaded plate thing, if you put a plate down here and then put another plate, let's say, let me do a better example. Let's say this is the first plate and this is the second plate. You put the second plate on, the first plate moves down. That's not really how a stack works. Okay? So when implementing a stack, don't think of it like that. Think of it like a stack of plates at home. Okay? So let's say that you had a plate location where you put your plates. Okay? So here, I'm going to explain how the stack works. Okay? So let's say you had a plate here. Okay? So these plates are just, a stack is really a container for things. So here I have plates, okay? So let me get some different color markers. Okay, get a green one. Okay, this will do. Okay, so I put my blue plate on. Okay, so one of the operations you can do to a stack is push things on it. Okay, so I just push the plate onto the stack. Okay. Okay, I'll do another push. Okay, I'm going to put it in a black plate. Okay. Okay, let's do another push. Push the green plate. Okay, so I'm pushing things on the stack, and notice how the first one I pushed on is on the bottom. The one I just recently pushed on is on the top. So let's say I pushed on another blue. Excuse me. Okay. So, like I said, one of the operations of a stack is to push things on it. So when you push something onto the stack, it goes on the top. Okay? Okay, so another operation that a stack can do for you is you can pop things. Okay? So to pop things, what you do is, to pop something is the act of removing it from the stack. Okay? So let's say I wanted to pop something. Okay? So let's say I ask the stack to pop. Okay? So it will remove the least recently added element, and some implementations may return it to you, some may delete it and not return it. Okay? But let's say that for our implementation, it'll delete it and return it. Okay? Okay, the last operation a stack could implement is top. So for top, what it does is it'll get the topmost element. It'll just get the least recently pushed thing. Okay. So in this case, you'll give me the green plate. Okay. Okay. So that's a stack. Let's see. So in Java, I'm going to look this up in the Java API for you. Java API. Okay. So Java does implement a stack, and I'm just going to read the Java API for you. The stack class represents a less in first out. So that's what I was explaining about how when you push onto the stack, it is when you push onto the stack, it becomes the top element. Okay, and when you pop from the stack, it's the first element out. So this is called a LiFO structure. So the first thing that comes in, the last thing that comes in is the first thing that comes out. Okay. Okay. So as I was explaining these operations, Java does have a stack class, and it does use generics, so you can have a stack of anything. Okay. So E means any type. Okay. However, the functions I described for like all stacks, Java named them differently. So there is a method to test if the stack is empty. So it's called empty. So instead of top, Java calls it peak. Okay. So yes, the top functionality is implemented in a method called peak. Okay, so you can also pop, and pop is called pop, and it does return the element it just popped. Okay, you can push an item onto the stack, and they also implement one more function, which is not guaranteed that all stack implementations have. So it has a method called search, and what it'll do is it'll search the stack and find out where the item is. Okay. Okay. So that is a stack. Okay. Okay. Another data structure I will talk about is called a queue. That's spelled Queue. Queue. So it's basically pronounced like the letter Q. Okay. So what a queue is think about, so if you've ever been to the bank, let's say we had one teller to make this a simple example. You had one teller and you had a little line here and you had like people here. And they're all in the queue waiting for the teller. Okay, so when you come in, you have to go to the end of the line. Okay, so a new person comes in, they go and wait at the end of the line. Okay, and when the teller is done with this guy, he says next, and then this person will be the next person to go to the teller and get money or whatever it is they're doing at the bank. Okay, so as you notice, there are two operations you can do to a queue. Okay, one of them is called enqueue, which is the act of adding an item to the queue, and the other one is called dequeue, which is getting the next element from the queue. Okay, so unlike a stack, which is a LiFO structure, last in, first out, the queue is a first in, first out structure. So the first person that comes in is the first person that gets served. Okay? So that is a queue. Okay. So let's see. I don't believe that Java directly implements a queue. Okay, so queue in Java is an interface. Okay? Which means that which means that you'll have to use one of the classes that implements that interface. Okay, so really one of the ones I like to use. So you can't use a queue directly because it's an interface. Okay, however, LinkList is a class that implements the queue interface. Okay, so to use a linked list as a queue, okay, so to use a linked list as a queue, okay, so the queue class comes with methods that must be implemented by any class that implements the interface. Okay, so to add to a queue, it's not called enqueue, it's called add. Okay, so the enqueue, all you have to do is just call method add. Okay. Okay, so to dequeue from the queue, what you have to do is you would use a method called pull. Okay, so what pull will do is it will retrieve the element and remove it. Okay, so I'll do a little example of a queue. So let's say here's our queue. Let's say that we pull add 1. Okay, sorry about that. Okay, let's say that we add 2. Let's say that we pull. So if we pull, we get 1. So now that's removed. Let's say that we add 2, 7, and 9. 2, 7, and 9. Okay. Let's say that we pull. So now we get 2. Okay, let's say we pull again. We get the second 2. Let's say that we add 3. Okay, let's say we pull again. We get the 7. Okay, you get the picture? Okay. Okay. So I'll talk about one more class as a bonus. Okay. So there's a queue, but there is something called a priority queue. Okay. So a good way to think about a priority queue is, say that you had a printer. Okay. And the printer has several jobs, okay? So many people use this printer. So like say from the president all the way down to like a middle school student or high school student. So the jobs coming in have a priority, okay? So what they want to do is they want to have the most important jobs run first, okay? Because they're more important than you. They're like defending the country or saving the world. Okay? So the printer is going to print the most important jobs first. And if there are least important jobs waiting, they'll all be executed later. Okay? Okay. So let me do a concrete example. Okay. Okay, so we still have the enqueue and dequeue of a queue. Okay. Okay, so instead of just giving an item to enqueue, we wanted to give an item and its priority. Okay. Okay, so let's say that we have A and 7. Okay. So its priority is 7. Smaller priorities are better. Okay. So we'll have 7. Okay, so this gets added to the queue. Okay, so let's say that we added 4. B4. Okay, so let me put this in a different order. Okay, let's say B4. Okay, so if we DQ, we'll get B4 and not A7. So it's not really first in, first out anymore. It's most important first. Okay, Let's say we added C5, and that would go here. Let's say D10. Okay, let's say we DQ. So, like I said, this is not going to come out, but this one will. Okay, that job just got done. Okay, so let's say we add B1. Okay, that's more important. So let's say we DQ. Okay, that goes away. DQ, DQ, DQ. Okay. So yes, it remains in sorted order. Okay. So there are priority queues in Java. Okay. So I believe the class is called priority queue, and I believe you can use that class directly. Okay. So yes, it is a class. Okay. Okay, so yes, priority queue is a class. Okay. And you can use it in your code. Okay. However, there is one thing that you need to be able to use a priority queue class. Okay. So if you use a generic version, okay, so this right here, so whatever class you have there needs to implement a compare to. Okay, so what I mean by implement a compare to, I mean that this class needs to implement comparable. Okay. Okay. So to implement, so I'm going to give you an example of a class that implements comparable. Okay. So let's see. So let's do the person class from like the very first time I did this. Public person, public class person. And now to implement an interface, all you have to do is when you declare the class, say implements comparable. Okay, comparable is also generic. Okay, let me get some more space. Let's see. Okay, you can see it. So implements comparable person. Okay. So now we're saying that we will only compare this with people. Okay. So yes, interfaces can also use generics. Okay. So to satisfy this interface, all we have to do is implement a compare to. Okay. So since we use generics here, okay, so the function is, the method is public int compare to. And since we use a generic version, it will be passing a person. Okay. Let's say that all persons have height. Okay. So I'm going to declare a instance variable here. Okay. So what the compare to function will do is test if this element is less than, equal to, or greater than this element. So to let it know that it's negative, well, to let it know it's less, we just return a negative number. To know that they're equal, we return 0. And if they're different, we return a positive number. Okay. Okay. So how we're going to implement this? We just say return, and it's not picky about what negative number it returns. It's just that it's negative. Okay. So we can return height minus p height, and that will satisfy the comparable interface. Okay. So if this person's height is less than that person's height, then that's going to return a negative number. If they're equal, this will return 0. And if this height's greater than that height, that means that this one's bigger. So we return a positive number. Okay? Okay, good. So that's just a side note. if you want to be able to use a priority queue, whatever you use it with needs to implement a comparable. It needs to implement the comparable interface. Okay, so now let's put all this together. Okay, so you learned about graphs, you learned about stacks, you learned about queues, and priority queues. Okay, so back on the subject of graphs. Okay, so I'm going to describe a problem to you. Right? And we're going to solve this using everything we've learned today. Okay, say we had this graph. And I'm going to make this one fairly big. Hopefully that's enough. Some edges, good old edges. Okay, so this is like a maze with graph locations. So let's say this is A. Let's say that you wanted to find your way all the way to X. Okay, so you can visually look at this and say, okay, I'll go here, 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 and here. Okay, and that works. But now we need to be able to tell the computer how. So let's say we're here. How will we get here? Okay. Okay, so we can do this with a graph search. Okay. So there are two types of graph searches I'm going to go over. Let's see. One of them is called a breadth first search. The other one is called a depth first search. Okay. So given this undirected graph, how might we find a way from A to X? Okay. Okay. So here's how we're going to do this. Okay. So we're at A. Okay. So we have a source and we have a destination. Okay. At each step, we're going to say, hey, are we at X yet? If we're not at X, then we need to look at all of its neighbors. Okay. And then we move to that node. Okay. Then we say, hey, is this the element we're looking for? If it's not, then we look at all its neighbors, and then we go to one of them. Okay? We must take care that, let's say we're here, we go here, we say, okay, we're not at X. If we're not at X, we move here. Okay? If this is not X, we look at its neighbors. And we're smart enough to know not to go back. Because if we just go back and forth, that'll be bad. Because that'll be an infinite loop. Okay? But we must take care not to do something like this, okay? We're here. Okay, this is not X. We go here. Okay, we don't want to go back to A at this point because we already know that A is not X, okay? So this cycle may cause problems in certain cases, okay? So we're going to deal with that too. Okay, so let's code this up, okay? Okay, so before I begin this, we need a way to easily test if we have a set of things and we want to make sure that something's not already in the set. Okay, so I just alluded to what we're going to use here, and this is another little data structure called a set. Okay. Okay, basically a set is just a collection of things. It's not in any particular order. And the reason why we would have one of these things is that looking it up is very efficient. Okay. Okay, so one of the Java classes that implements a set is called a hash set. Okay. Okay, so this is a Java class implementing hash set, and like I said, what a set is just a collection of things that you can easily look up in it and find out if it's there. Okay, and it's more efficient than just using an array. If you had like an array, then you would have to go. Let's say that we wanted to set to D's in the array. We have to go and say, hey, is this D? No. Hey, is this D? No. Hey, is this D? No. And then we say, hey, is this D? And then it is D. Okay? So with the set, and you don't need to worry about the implementation of it. It's just O of one look. It's just an O of one or O of n lookup, depending on how it's implemented. Okay. Okay. So now we are going to code a graph search. Okay. The first graph search I'm going to cover is a depth first search. Okay. So how we do a depth first search is, okay, we say, hey, we're at A. Okay, so we're going to get its neighbors. Okay, we don't necessarily care which one we choose because we don't know which one is going to lead to X. Okay, we're going to do this in a different color. Okay, so what a depth first search is we'll say, hey, okay, let's take this edge. When I do that, I'm drawing these out in like a different color so you can see. Okay, so now we're at this edge. Okay, so now we say, hey, what are its neighbors? So we don't want to go back because we marked this as visited. Okay, so we already visited this. Okay, so when we visit a node, we say, hey, it's visited. Okay, and then we'll say, okay, give me its neighbors. Okay, so we get this one. Okay, we want to go here now. We mark this as visited. Okay, so now we say, okay, we're here. Where are its neighbors? Okay, so now we get this one. But hey, this one's already been marked. So we don't want to visit that one again. Okay, so like I said, we'll store all of our nodes in a set. And this will allow us to easily test pretty efficiently whether we already visited it or not. Okay, so now we're here. We say, we don't want to go here. Let's say we want to go here next. Okay. We're now here. Okay, we go here. We choose one. Okay, so let's say we choose this one. And then we go here. Okay, we're here. Okay, let's say we get all the neighbors. Okay, we choose this one. We go to it. And yeah, we're marking these as visited as we go. Okay, we're here. We only have one node. Okay, so we mark this as visit. Okay, we go here. And now we see we're at X. Okay. Okay, I'll do one more example since I showed a path that led to the answer. Okay, so suppose at this first step, we were at A, and then we just get all the neighbors, and we just pick one at random. And let's say that we do a depth first search, okay? So we mark this one as visited. So I did this search in green. And we get all its neighbors, and we say, oh, hey, let's go this way. Okay, we mark this as visit, and we get all its neighbors, but hey, there are no neighbors. Okay, so since there's no neighbors, we need to backtrack. Okay, so we're back here, and we say, okay, so that didn't work out. So let's find another neighbor. So let's say we go this way. Okay, so we can backtrack and go back to places we already visited and just go to its neighbors. Okay, so we'll handle that in our code. Okay. Okay. Let's see. Okay, so I'll drop another graph later. Okay, so now let's write some code. Okay, so depth first search. We're going to be taking in a graph. So we're going to call this public Boolean. And this is abbreviated DFS. Let's see. Sorry about that. You can't see that. Stand up. Public Boolean DFS. Okay. This is going to take in a graph. Say node starts. See that. Okay, run out of space. So starting node ending node, and that should do it. Okay, so like I said, we want to initialize some variables. Okay, so how we're going to do this is we're going to use a stack. So we just learned what a stack was. So stack. Okay, this will be of type node. And I'm just going to call this toVisit. So we'll have a stack to keep track of where we are. Okay, so now let's see. We will create a hash set. And don't forget to initialize these. Hash set of nodes. This will be a hash set of nodes that have already been visited. So I'm going to call this marked. Okay. So first we start out at the starting node. Okay. So sorry about that. Okay, so we start at the starting node. Okay. So I'm also going to have a node cur. Actually, I'm not going to do that. Okay. What I'm going to do is I'm going to push this onto toVisit. So this was add. And sorry if I don't get these 100% correct to the Java API. I'll just name it the things I named it when I was describing these data structures. So I'm going to push it onto the stack. And I'll leave it as an exercise for you to come up with the code for this. So push start. Okay. So what I'm going to do is I'm going to start it out by pushing this onto the stack. Okay. I will also have a current node. I wanted to initialize this to null. Okay. And I will also have a found variable to let us know if we found it or not. Okay, initialize this to false. Okay. So while not found, okay, while we haven't found it, and we don't want to pop from the stack if it's empty. So let's handle that. Yeah, it's not empty. So while we haven't found the element we're looking for yet, and our stack is not empty because we don't want to pop from an empty stack. Okay, so now we are guaranteed that 1, we hadn't found it. 2, we have an element in our stack. Okay, so what we do here is we say cur is equal to stack pop. So we pop it from the stack. So this will give us a node. Okay. Okay, so now we check if cur is equal to our destination. So n. So if cur is equal to n, or it would be better in Java to say dot equals. Okay. So we're assuming that node class has a dot equals method. Okay. So if cur is equal to n, we say that it's found. And it wouldn't hurt, but you can also break out of the loop. You don't have to have the break statement because if we set found to true, the next iteration, it'll break out automatically. But yeah, break is optional. Some programmers don't like to use it. I don't really care. And this is a programming competition, so just pick something and stick with it. Okay. So if we don't go here, that means that we haven't found it yet. So now what we can do is we can say, and also right here we need to mark it as visited. So we would say marked, and hasset has a method called inserts. So a property of a hasset is once you insert it, it's in the set. If you insert it multiple times, it'll only be in there once. Okay. Just a side note. So we need to insert cur into our hasset, which means that now we're marking it as visited. So now we're at this node, we're marking it as visited. We then check if it's our destination. If it's our destination, we say found is true, and then we break out the loop. Okay, so if it's not our destination, what we have to do is we have to look at its neighbors. We look at its neighbors. We then choose one of its neighbors. And we then... Sorry, one second. Ooh. Okay, like I was saying, what we're going to do is we're going to add all its neighbors to the stack. So we're going to push them all onto the stack. And we push, the last one we push in is going to be the path we choose. Okay? So it doesn't really matter how you do this. You can do it randomly if you want, but it doesn't really matter. Okay? So we do for. Okay, so a for loop in Java, you can do it this way. This is called a for each loop. For node A and graph, we'll say, okay, I call it the graph A. So for node N and A, remember that A is a graph. I named it A for some reason. So A that get neighbors. Remember that get neighbors method we coded earlier. Get neighbors for cur. Okay. So here we need to check. We need to test if the neighbor has already been visited. Okay. Here's one more. Okay. So if marked. Okay. So if not marked. And hasset has a method called contains. Let's see. N. So if it's not contained in the hasset, what we do is we say to visit push in. Okay, that's it. Okay, so now we handle the case if we break out the while loop. If we break out the while loop, we just return found. Okay, so here's our code. Okay, so I'm going to move over so I can show you a demonstration of why this works and how it's working. Okay, sorry about that. I'll show the code a bit later. Okay, let's see. Okay, so let's get a graph again. Okay, undirected graph with no weights. Let's say this is A, B, C, D, E, F, X. Okay, so here's our graph. Let's say that our starting node is A. Say our destination is X. Okay. Okay, we'll have a stack here, we will have a stack. Let's see if you can see that. Okay, cool. So here's our stack, and here's our hash set of visited. Okay. So we start at A. So we started out in the code. We said toVisit.push start. Okay. So we go to our stack. Okay. Start is A. So now we push A onto the stack. Okay. So now we are in the while loop. So at each step of the while loop, we said, okay, we take the element, we take the topmost element, and we pop it. Okay. So now we pop A. So now cur is equal to A. Okay. Okay. We then marked it. So now A is in our marked list, which we'll see marked. And here's toVisit. Okay, we then said, hey, if current is equal to n, we say found true, it's not equal to n. Okay, so now we look up A's neighbors. Okay, sorry about this. Okay, we mark A as visited. So I'm going to denote that on our graph here. Okay, we then get all its neighbors. Okay, so in this graph, the neighbors are B and D. Okay, both of these have not been marked yet. So I'm going to do this in order. So let's say B and D. So we push B onto the stack, we push D onto the stack. Okay, so now we are done with the iteration with A. Okay, so we hadn't found it yet. So now we're in the second iteration. So we take the top element off the stack. So now we have D. Okay, so D is now off the stack. Cur is D. Okay, so now we say, okay, D is now visited. Okay, we now have D here. Okay, so this is not the element we're looking for. Okay, so now we get neighbors. So now we get A and C. Okay, so now notice that A has already been marked. So that does not get added to the stack. So now we have added C. Okay, so now C is on top of the stack. So now we say, okay, next iteration, we say, okay. We pop from the stack, we get C. So now current is C. Okay, we mark C as visited. Okay, so now we're here. Okay, so is C the element we're looking for? No. Okay. Okay, so now we look at C's neighbors. Okay, so we see that we have B here. So B is already in here, but we're just going to add it onto the stack. Okay. Okay, so we're going to add it onto the stack anyway. So B, and we're going to, well, to make this example more fun, I'm going to add E onto the stack first. So you can see what happens when we actually exhaust all our paths. Okay, so E, then B. Okay, so notice that we have 2 copies of B on the stack. It doesn't really matter. Okay. Okay, so we're done with C. Okay, so now we pop the top element off the stack, we get B. So now we're finally visiting B. Okay, so now we mark this as visited. Okay, but B is not the element we're looking for. Okay, so B is not the element we're looking for. Okay, so now we say, okay, we look at all its neighbors. So we have A and C, but both of these have already been marked, so nothing gets added to the stack. Okay, whoops, we have to remove that. So nothing gets added to the stack. Well, we didn't actually do anything useful in this iteration. So now, okay, so now we go back up. Next iteration, we say stack pop. Okay, so now we're at E. So if you look at this, we actually did something. Let me get the red marker. Okay. So here's how we traverse this graph. We went this way, we went this way, and we went this way. Okay, but now we are going back. Okay. So that's how the go back works. Okay. So now we're testing C's other neighbor, E. Okay, so now we pop the E off the stack. Okay, so current is now E. We put E in marked. Okay, so now we do this. Okay, and now we went this way. Okay, so it's E the element we're looking for. No, it isn't. So now we push all of E's neighbors onto the stack. So now we get a X and an F. Okay. Okay, so now going faster because you should get the picture by now. Okay, so now we pop from the stack, we get F. Okay. We mark F as visited. Okay. So F has no neighbors, so we do nothing. Okay, we pop from the stack, we get X. Okay. So we mark X as visited. Pop X off. Okay, so now we're at X. We're like, finally, we got the X. Great. Okay. So now we're at X. Found is set to true. And then we break. So now we're done. Okay, so we return true. Okay. So say that there was actually no connection to X. So what would happen is if we were at E, when we push off E's neighbors to the stack, we get F. Okay? So when we get F, so F is already visited. Well, if we get the F, we mark it as visited, and then we add all its neighbors, and we won't add anything. So then we pop it off, and then we see B here. And we should add some code here to test if we visit a node that's already, if we pop a node that's already been visited, we just see nothing. Okay? In this case, if we go to a node that we already visited, then all its neighbors already visited. Okay? So in that case, our stack will become empty and we return false. Okay? So that is depth first search. Okay? Okay, so if you notice the property of depth first search is you just continue going on that path. So you just continue walking. So if you're in the maze, you would be doing a depth first search because you would just take a path. You keep on taking paths with the path that you already took. Okay? And if you run out of paths, you just backtrack and then take another path. Okay? Okay. Okay, so the other type of search is called a breadth first search. Okay? So I'm not going to bore you with the details of the code, but if you had this boilerplate code for depth first search, all you have to do is just the power of magic on the board. Okay. So remember the queue? Okay, instead in Java you would say LinkList, and instead of push and pop you would say NQ and DQ. But there are very small changes you have to do to turn this into a breadth first search. Okay? So, as I said, push becomes NQ and pop becomes DQ. Or in Java's case, push becomes add and pop becomes poll. Okay? Okay, so we can go back to the graph. And I'll show you how breadth first search is different. Okay. Okay. Okay, so we're going to use the same graph. Erase it first. Same parameters. Same graph, same parameters. Except this time we are going to use a queue and not a stack. Okay, so here we are going to have a queue, which I'll denote by these brackets. Okay, you can see it. Okay, start at A and we end at X. Okay, so we do a similar thing. We push our first element onto the queue. Okay, so now we start the loop. Okay, so we say A. Okay, we DQ A. So now current is A. Okay, we mark A as visited. Okay, I don't want to do this in fancy colors this time. Okay, so now we visit A. So now we enqueue all of A's neighbors. So B and D. Okay, so now we DQ. Now we get B. Okay, we mark B as visited. And our current is B. Okay, so for B, we know that it's not X. So now we enqueue all of B's neighbors. So now we have C. Okay, so now we DQ. So now we have D. Okay, so for D, now we DQ, and now we get D. Okay, so now we enqueue all of D's neighbors. Okay, so we put in C. So now we have two C's. Okay. So now we DQ, we get C. Okay, now we push all C's neighbors. Whoops. So now we get E. Okay, mark that as visit. Okay. So now we DQ again, we get C. So, like I said, if we have C, if you visit a node, if you DQ or pop a node that's already been visited, you just say, okay, throw that one out. Okay. Okay, so now we have C. Okay, so we have C, we throw that out. So now we're at E. Okay, we DQ, we get E. Put in all these neighbors, so F and X. Okay. Okay, so now we DQ, we got F. F has no neighbors, so we do nothing. Okay, so now we get X, we DQ it. Okay, that's the element we're looking for. And we found it. Okay. Okay, so one of the properties of a breadth first search is, okay, so we look over here, and then we look over here. Okay. We go this. Yeah, we look over here, we check all of A's neighbors before we check all of B's neighbors, and before we check all of D's neighbors. Okay? So it's breadth first. Okay, okay, so we go here and here, then we go here, then we go here. So if you notice, this is, we check everything 1 away from A. Then we check everything 2 away from A. Then we check everything 3 away from A. So that's how breadth first search works. Okay? Okay. Okay, so the last type of search I'll leave as an exercise for you guys to play around with. So if you remember this boilerplate code for a breadth first search, yes, you can turn this into really any kind of search. So if you use a priority queue that I've been talking about instead of a queue, you'll get something called a best first search. best first search. Okay, so you can use a best first search on a directed graph. Okay. Okay. So yeah for best first search, what you have to do is so you'll have to make two changes to this code. So for a queue, instead you use a priority queue, and when you push nodes onto your priority queue, that priority will be the total length you have traveled so far. And if you use a priority queue and make this change, you will solve the problem of how to get what's the quickest route to two cities. Okay? Okay. Okay, so I'm going to discuss one simple problem, and that will be the end for today's lecture. Okay. Okay. Hopefully this time, well, okay, I'll just put up a website that you can go to find this problem. Okay, it's a simple problem, and it applies all this knowledge you've learned. Okay. Programming team .cc Caltech edu / contests / making sure that you can all see this. GT Spring Feb 16, 2012. Okay, / problems / problems.pdf. Okay. You can feel free to do all the problems in this problem set. The one I'm going to be looking at is problem G. Problem G is an application of all the stuff I have talked about today. Okay, so problem G is called getting gold. Okay, so I'll read out the problem description for you so you can follow along if you're like following along. So the problem states, we're building an old school back to basics computer game. It's a very simple text-based adventure game where you walk around and try to find treasure, avoiding falling into traps. The game is played on a rectangular grid, and the player gets very limited information about her surroundings. The game will consist of the player moving around on the grid for as long as she likes, or until she falls into a trap. The player can move up, down, left, right, but not diagonally. She will pick up gold if she walks into the same square as the gold is. If the player stands next to like immediately up, down, right, left, just like one square away from one of the traps, she will sense a draft but will not know from what direction the draft comes or how many traps she's near. Okay? So rectangular grid. Okay. So what this is talking about, the player can be right here, but there can be a trap right there, but she doesn't know the trap is like from the right of her, to the right of her. Okay? And there could be multiple traps, so she could be like that. Okay? But if she walks into a trap, she loses. So we don't want that to happen. Okay. Okay. Excuse me. Okay. For scoring purposes, we want to show the player how much gold she could have gotten safely. That is how much gold the player can get playing with an optimal strategy and always being sure that the square she walked into was safe. The player does not have access to the map, and the maps are randomly generated for each game, so she has no previous knowledge of the game. Okay? Okay. So this problem has input specifications, so you'll get two integers, W and H. They will not be smaller than 3 or larger than 50. Okay? So this is the width and height of the map. Okay? So the next H lines will contain W characters each, which will give you the map. Okay? So there are also symbols. So you have the player, a piece of gold, a trap, a wall, and a normal floor. Okay? There will only be one player on the map, and there will always be walls. Okay? So we need to output the number of gold pieces the player can get without falling into a trap, or without risking falling into a trap. Okay? Okay, so there are some inputs. Okay, so here's one. So it's 7, 4. 1, 2, 3, 4, 5, 6, 7. Okay, 2, 3, 4. Okay, here's a player. Okay, here's empty spots. So this match up. Okay, more walls. Okay, you have a gold piece, 2 traps, and 3 more gold pieces. Okay, so following the rules of the game as a review. Okay, so we want to get the maximum number of gold pieces, but we don't want to go into a trap. Okay, and if the player is next to a trap, she'll know. Okay, so if the player does not sense a trap, that means that there's no trap there. Okay, and the player can go to a gold piece that's next to a trap. Okay, so the output for this one is 1. So you can do this, but you can't go past here because there are 2 traps. Okay. Okay, another input, which is a little bit more complex. I'm not going to draw out all the symbols this time. Okay, so you have 8, 6. So here's a wall. So this is 8, 6. Okay. So you have a gold piece, trap. Okay, so you basically have 4 gold pieces at this end. Okay. Trap here. Okay, so player is here, G, T, and there's a wall. Okay. So the answer to this sample input is 4. Okay. Okay, so how this one works. So you can move here, get this gold piece. You can also move here and get this gold piece. Okay. So you can get 2 gold pieces because Don't want to be here, here. Okay. This one takes a little bit of thinking. Okay, so you don't want to. So here's the problem. So you want the number of gold pieces she can safely get. Okay? So she can safely get those two. Okay? But if you move here, you don't know if there's a trap here or anything good here. You don't have any information about the map. You can just move up, down, left, right. But if you're next to a trap, you can sense a trap. Okay? Okay, she can also get this gold piece. So she can move up here and then move here. So that's 3 gold pieces. She can get this one, this one. Okay, and the last gold piece, if she moves here, 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 she moves down from here, she can get that one. So the gold can be next to a trap, okay? As long as, so, think of an example of this. So if there's a trap here, she wouldn't want to move. Let me see. So let's say that the player was here. So she's not here. She's moved one over, and there's a trap right here. So if she moves here, she'll notice that there's a trap. So she doesn't want to go here or here. But she can move up here, get that one. But she knows that there's a trap here, so she doesn't want to get that one because there could be a trap right there. Okay. Okay. So here is a solution for this problem, and I'll tell you the basics of the solution, and I'll leave it up to you to actually code it and test it. Okay, so let's go back to the first map. See, it was 7 by 4. So how you can do this is when you enter in the traps, so you're given a map and you have to tell, and you have to output how many gold pieces can she get safely. So the player is going to be moving, but she doesn't have the information about the map. But you're a coding solution that has a map, but you're controlling the player who does not have information about the map. Okay, so you'll initialize a 2-dimensional array containing what's there. Okay. Okay, so you'll start out by putting in the walls and you put in the traps. Okay. However, when you put in the traps, what you'll do is you can put in another symbol, let's say C, which stands for close to a trap. Okay, so what you'll do is you'll put a C here, a C here, and a C here. Okay, so this trap, let's see if I'm making this, crap. Okay, actually, let me make this better. There's a P here. Okay, so you start out by putting in the walls and the traps, okay? Now for each trap you put in, I'm going to put in another character called C. So C here, C here, C here, and a C here. So you put this around the traps, okay? Now make sure that you don't put this outside the bounds of your array. So you'll have to do a check for that, okay? So you'll put one at, so let's say that you had an XY. Okay. So you'll put one at X minus 1 y, x plus 1y. So x minus 1y, x plus 1y. And as long as x minus 1 is greater than or equal to 0 and x plus 1 is less than the array's width, you can put it in. Okay. You also do y minus 1. So if y minus 1 is greater than or equal to 0, you put it down. If y plus 1 is less than or equal to if it's less than the height, then you can put one down here. But if you put one down here, then you'll run into an index of the pounds exception. Okay, another way to handle the putting down thing is you can do what you can do is you can pad it. So you can pad it with link 1 and all these will be 0. Okay, and then you can write to it safely. But make sure that the player doesn't actually go outside the bounds of your map. Okay. Okay, so you place down the traps first, and then you place down all the gold. Okay. So in this case, there's a gold piece right here. So the C will be replaced by G. Okay. These C's will be replaced by G's. So G's overlap C's. But you do start out by placing the traps, and then you place down the C's, which means that you're close to a trap. Okay? Okay, so when you're close to a trap, you want to go back. Okay, because you don't know if you go here, you don't know if that's a trap or that's a trap. You have no information about the map. Okay, so the player's starting location is here. Okay, so now if you notice, you can represent this as a graph. The graph being the player state will be an X and Y. So you can do a breadth first search. Okay, so how you would do this is you would go here. Okay, go here. Okay, so I go here, so I'm not at a C. And now I could go here, I'm not at a C. And now from here, I move here. So that's a C. So I don't want to move from this place to go anywhere else. Okay, so here I don't push in any neighbors. But here, okay, so I already visited down here. So I move this way, then I get a G. So now when I'm here, I can go down. Okay, actually, I made a mistake in my initial solution. Actually, you do need to keep track if this. You'll have to add some information that this is a C and a G. Because if you don't do that, then what will happen is you'll get here, and you'll say, okay, that's a G. That means I can move freely from anywhere here. And then you'll run into a trap, and then game over. Okay, so you don't want to do that. You actually want to keep some metadata saying that was a C. Okay, so sorry about that. G's don't overwrite C's. So you need to keep track if that's close to a trap. Okay, yeah, sorry about that. Okay, so this place was marked as close. Okay, so good thing about testing this is that you'll find your mistakes when you're talking about it. But yeah, this is a C. So since this is a C, you don't want to NQ this, you don't want to NQ that. Okay, so you're done. So you output 1. Okay, so this is actually another type of algorithm which is based on a breadth first search. It is called a flood fill. Okay, so I'll work this out as the last thing I'm going to do for this one tonight. I am going to work out the other one to just show you that the answer is 4, and then I'll leave it to you to come up with the code for this. Okay. 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 So this problem was, let's see. Okay, so here's a wall. 1, 2, 3, G, T, G. Dot, P. G dot G dot 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 G wall G. Okay, last one. Dot dot T G dot G. Okay, so like I said, when placing the traps, you go and you place metadata on these tiles that the trap is around. So C, C, C. Okay, I should probably do this in a different color. C, C, C. Okay. There's another trap. C, C, C. Okay. Okay. Okay, so here's the player. So like I said, you're going to do a flood fill. Okay. So like I said, flood fill is using a breadth first search. Okay, so this is a node. You can treat these locations as nodes. Okay. So when you're at a node, its neighbors are going to be one up, one to the left, one down, one to the right. Okay. So let's say that we go this way first. Okay. Hey, we got some gold. Great. Okay. So now let's say we've marked this as visited. So I'll do this with like little dots. Okay. Okay. So as part of the breadth first search, we now go down. So we're now testing everywhere that the player can get to length one away. Okay, we go here. Okay, actually. So when we go here, we add these three to our queue. Now we move down, we say C. Okay. Okay, now we're at a C, we don't want to do anything. We don't want to move anywhere differently from this spot. So we don't NQ anything. Okay, now let's test up. Okay, if we go up, we mark this as visited. Okay, so now we put this one into the key, we put this one into the key. Now we go this way, mark this as visited. Okay, we put this one into the key, this one into the key, this one into the key. Okay. So now that we visit everywhere of link 1, now we visit everything of link 2. So let's say we go up here first. Okay. We get some gold. Yay. Gold. Okay. So now, but this is a C. We don't want to move anywhere from here. Okay. So now that's a C. We don't do anything. Now we move this way. We go here. Oh, we say, uh-oh, that's a C. Okay, so we don't want to move from here. Now let's say we go down, we get some gold. Yay. Okay, so now we try to go this way, but we can't go this way because that's a wall. Okay, so we add this way to the, well, we don't add this way because we're already visited. Now we can go down from here. Okay, now we go this way, do this way. Okay, that's good. Okay, here, we can move up, well, move up, move to the left, move down. And just going to speed through this one. Okay, so you can move up from here. And I may not be going in order, but eventually, what a flood fill is, say that you're like pouring water, and basically everything that you touch turns into water. Okay, so a good way to demonstrate flood fill is, let's say that you were in paint. Let's see if you can see this. Okay. Markers. Okay, where did my markers go? Okay, say that you had a little picture. Okay, here's my picture. And notice that this is all white. This is all white. So flood fill, you just give it a position, and then you say flood fill. So it actually goes kind of like this. It goes everything 1 pixel away, everything 2 pixels away, everything 3 pixels away. So if you actually look at it, it will kind of actually fill it like this. You start here, everything 1 pixel away, 2 pixels away, 3 pixels away, 4 pixels away. So it'll actually in reality look like a diamond. Okay? Okay, so that's what Phil. So if you code up this algorithm and use it at the player, if you get to an element that you're at C, then you don't actually want to enqueue any of its neighbors. Okay, you just want to stay there. Okay? Okay, so I hope you learned a lot from this exercise, from this lecture. I hope you learned a lot about data structures because they are really useful in these algorithms. So if you learn how the data structures work, you learn which one to use in a particular situation, then it will only help you solve problems. Okay? So this has been Brandon, and bye.